So, we discussed now how to deal with local constraints or function type constraints. Let us solve one example to understand what this means. Let us go back to the example of what I had called Chatterjee's problem. Okay. So, let us write that Chatterjee's problem. This is after Anindya Chatterjee is a professor in IIT Kanpur. In my discussions with him, this problem had emerged, so I continue to call it as Chatterjee's problem. So, that problem is that I am showing the roads that we had discussed earlier as axis now. There is x axis and there is a y axis. I need to find a function y of x such that there is a river flowing. Okay. Let us say this is the river r of x, okay. And there are some limits, that is 0 to some h here. Okay. Now, I need to find a function y of x. Okay. I need to find that function y of x in the limits 0 to h such that, let us say I say this function y of x like that. This y of x has to be below r of x, because we said there is a river flowing. So, let me show it like a river. There is some muddy water. Okay. It has to be below that, and the farmer who is asked to take as much land as is given by the government. Let us say that is some A, the land A, this area under the curve is A, that is given, let us say that is A star, okay, that is given. But this farmer can take A star land within this domain 0 to h, but has to be below the river. What should be the curve which will be the boundary of this? There are already these boundaries, this is a boundary, this is a boundary. If there is this height, that is also a boundary, but the new boundary has to be chosen. The farmer wants to take A star area land, but he or she wants to minimize the fence length, that is the length of the fence. So, that problem we can pose as minimize length of the fence, or for a given fence he or she wants to maximize area. Let us write it that way. So, not minimization, okay. Let us actually pose it as maximization, maximum A, okay, not A star. Let us say this farmer says I have budget of only so much to spend on building a fence, which is this y of x function. So, here she wants to maximize area. So, area will be y dx. Area is y dx from 0 to h, right. If we have such a thing here, our unknown here of course is y of x, right. So, when we have this problem and we have some constraints here, right, subject to, we have subject to the fact that y should be less than r, less than or equal to, because the river is there, y his or her fence cannot go into the river. We have this constraint, which is a local constraint, because this should be satisfied at all points in the domain, at all points in the domain. It is a local type constraint or a function type. There is no differential equation, right. So, there is simply y of x minus r of x is less than or equal to 0, right. That we discussed already how to deal with that. There will be a corresponding Lagrange multiplier function there. We also have the constraint that farmer has imposed, which is the length of the fence. Length of the fence 0 to h 1 plus y prime square root dx minus some L star that is chosen is less than or equal to 0. This is a global constraint right. So, this is a global constraint or a functional type constraint. Okay. So, we have chosen a problem which has both a local constraint and a global constraint. Okay. Again, how does this constraint come up? This is because of the fence length of the curve, that is square root of dx square plus dy square. We have taken dx out, that becomes 1 plus y prime square dx. Okay. And what is data for this problem? We are given h and we are given this r of x, river profile and L star. Okay. These are the things that are given to us. We need to find y of x. Okay. One thing that we would change is that whenever we maximize something, our convention is always to minimize. So, let me change that maximization to minimization, but I will put a negative sign. Okay. Minimizing negative area is equivalent to maximizing positive area. So, our problem now becomes again to have continuity, right. So, we have that, right. So, we would write the problem minimize minus integral y dx, that is the area enclosed from 0 to h. Our unknown function is y of x subject to y minus r less than or equal to 0 and then 0 to h square root of 1 plus y prime square dx minus L star less than or equal to 0, and do not forget to write the Lagrange multipliers lambda x and lambda. Okay. When you have this, the first thing we do is to write the Lagrangian, which is 0 to h minus is there y dx plus 0 to h lambda times y minus r dx. Note again that this constraint, this local constraint should be valid for all points in the domain. So, we have to integrate after multiplying the corresponding lambda. Lambda is also defined everywhere, this constraint is also defined everywhere. We multiply everywhere and add, because ultimately our Lagrangian is a functional, it should be a scalar. Okay. Plus we have this other one 0 to h capital lambda square root of 1 plus y prime square dx minus lambda L star. Okay. Well, this is not Lagrangian L star, this is simply length star. Okay. This length here, that is not the Lagrangian. Lagrangian we have slightly scripted L. Okay. This is the thing. Now, in order to solve the problem, I have this function y of x. Here what is given? The data we should always write. We had written above, we will write again. We know h, we know Rx and we know this L star here. Okay. Local constraint, which is an inequality, that is a difference. You see, if we have equality with only one function, this would have been an improperly posed problem, but what we have here is an inequality. When you have inequality, if you recall what we had discussed in one of the earlier lectures dealing with finite variable optimization, when you have inequality, we write what is called the complementarity condition, that says lambda times y minus r is equal to 0. Again, this is applicable for all points in the domain x1 to x2. This is called complementarity condition. Complementarity condition. Okay. That means that either lambda is 0 or y minus r is 0 at different points in the domain from 0 to h in this problem. Okay. So, if we go back to the problem, if we say y minus r equal to 0, that means at some point the function may just follow the river. Okay. So, here we say the constraint is active constraint, right. In other places, if it deviates from it like that, in this portion this is active. Okay, let me put it in blue. Other portion, let me write in red, it is inactive, right, where y is less than r, that river profile, right, whereas in some portion it is just equal. In that portion where it is active, the lambda that we have need not be 0, because complementarity condition says that either lambda is 0 or y minus r is 0, because their product is 0, right. So, when lambda is 0, it makes the constraint inactive. In such a portion, in general, y minus r is less than 0. It can be 0 in some special cases, in general it is not. On the other hand, if lambda is not equal to 0, implies that the constraint is active. That also means that y minus r must be equal to 0 because of the complementarity condition. Okay. So, for this problem we can write the necessary conditions. Okay. We can write the necessary conditions in the manner of KKT conditions for calculus of variations, that is Euler-Lagrange equations plus KKT conditions. That is what we mean by necessary conditions for this problem. If we do that, we have this Euler-Lagrange equation. If I write, we have in the Lagrangian, we have this entire integrand. Let me write that integrand. Let me write the Lagrangian here. Lagrangian 0 to h minus y from the objective function lambda times y minus r, okay, and we have capital lambda times square root of 1 plus y prime square dx, and then we have this lambda L star. Okay. Basically, I have collected the terms that were here. We wrote this one, we wrote this one, we wrote this one, and then we also wrote that which is immaterial. Let me, yeah, this is our Lagrangian. So, now what is f? The integrand is this. When I write Euler-Lagrange equation, I have to write dou f by dou y minus dou f by dou y prime whole thing prime d by dx of that equal to 0. We only have y and y prime here in this problem. We do not have y double prime and other things. Okay. That is true. And we also have the constraint. When I write KKT conditions, I have to write the constraint also 0 to h square root of 1 plus y prime square dx minus L star equal to 0, and we have our inequality constraint yx minus rx is less than or equal to 0, and then we also have the complementarity condition, which is lambda times y minus r equal to 0, and as complementarity condition arises with inequality, we also have this other thing that lambda of x is greater than or equal to 0. It cannot be negative for the same reasons we had stated for finite variable optimization. Okay. So, now we have some equations to solve. Our unknowns are, again let us see what our unknowns are. Our unknowns are clearly y of x, and also we have lambda of x that is not known, right, and we have this uppercase lambda. These are the things that we do not know. In order to solve for y of x, which is a function, then we need a function equation or a differential equation. We have a differential equation here. Okay. Now, in order to solve for lambda, it is a scalar unknown, we need a scalar equation which we have, and for lowercase lambda, that is this one, we have a function type constraint which is this, and this complementary condition gives rise to two cases, either lambda is 0 or y minus r equal to 0, and then this automatically gets ensured. So, this gives rise to two cases, case 1, case 2. One is lambda equal to 0, other is y minus r equal to 0, where y minus r is easy to deal with. We get a y already, y is r, that means that you follow the river profile. Whenever you do not follow the river profile, then lambda equal to 0, the constraint becomes inactive. Okay. So, let us first write this Lagrange equation that we have here for f. Remember, our f is minus y lambda times minus y plus lambda times y minus r plus capital lambda times square root of 1 plus y prime square. Okay. Let us finish up this problem. So, I will write f minus y plus small lambda times y minus r plus capital lambda times 1 plus y prime square. Now, what I want to write is dou f by dou y minus dou f by dou y prime prime equal to 0. That means, if I want dou f by dou y, y is over here, that gives me minus 1, but also get y there. So, I will get plus lambda, okay, minus 1 plus lambda, and that is it, there is no y, there is y prime here. So, I have to write minus dou f by dou y prime, that will give me lambda, I am taking derivative of this one with respect to y prime, that will give me 1 plus y prime square square root, there will be a half here, there will be a 2 y prime, let me write it anyway, and 2 y prime, because take derivative with respect to y prime, there is y prime square there, that gives 2 y prime, and this 2 get cancelled, okay, and this whole thing derivative, that is what we have here, right, that prime, right, that is equal to 0. In other words, what we are getting here is minus 1 plus lambda minus lambda times y prime by square root of 1 plus y prime square 0. Okay. Let us expand. This is a necessary condition. Let us see if there is a solution lying in front of us. So, let us take this derivative of this. Okay. The derivative, if I take lambda, we have we use the quotient rule here. So, that will give us 1 plus y prime denominator, derivative of the numerator, and then minus the numerator time derivative of the denominator, that will give us, we already have done that. So, that will give us divided by square root of 1 plus y prime square, half, and this will go, we will have y double prime there, we take derivative of that y prime thing, divided by square of the denominator, that will become 1 plus y prime square, that is equal to 0. Okay. Now, if we further proceed, minus 1 plus lambda minus lambda, if I take LCM of the top portion, that will give 1 plus y prime square into y double prime. So, let me write that. So, it will become 1 plus y prime square into y double prime minus okay, y prime. Okay, here I will get y prime, there will be another y prime when I take derivative, that becomes y prime square y double prime, I suppose, yeah, and in this here we will get 1 plus y prime square raised to 3 by 2, because we already have this, and then this is coming together, that is equal to 0. So, if I do this further, minus 1 plus lambda minus capital lambda, here y primes y double prime will get cancelled. So, what I will be left with will be y double prime divided by 1 plus y prime square 3 by 2 equal to 0. Okay. That is what we get. Now, we have two cases, right. So, one case is lambda equal to 0, other case is y minus r equal to 0 or y of x equal to r of x. So, in the domain 0 to h, we have two possibilities. One is the function y of x is equal to r of x, solution is known, we follow the river profile. Other is lambda equal to 0. If I substitute for the second for the first case lambda equal to 0, right, then minus 1 minus lambda into y double prime plus 1 plus y prime square 3 by 2 equal to 0, or in other words, if you notice what this is actually curvature, right. In your beam theory you would have used this result many times. Y double prime divided by 1 plus y prime square raised to 3 by 2 is curvature. What this is saying is that whenever you do not follow the river profile, you should choose a curve which has constant curvature. Because it is constant, because there is lambda and there is minus 1, everything else is constant here. So, this curvature is not a function of x, right. Curvature is constant. When curvature is constant, what should be that curve? That curve should be a circle, right. So, the answer to what we call the Chatterjee's problem, if I have x and let us say this is the river function, this is r of x, and we have to be from here to here only. So, this is fenced in. Now, if you want to solve this problem for a given fence length, okay, you have to, let us say, whenever you are not touching the curve, you should be a circle. If the circle goes like this, that is you are going to enclose the maximum area, that we know, that is a perimetric problem. Instead, if your thing comes out to be in such a way that let us say river profile, let me change the river profile a little bit to make our point. Okay. Let us say the river profile I do like this. All right. Then let me erase what I have chosen earlier. Okay. So, our thing, this was our answer, but that will not be allowed now, because we are going above, we should be below the river. So, this is not allowed. So, in this portion what happens is this portion is not allowed, we just have to follow the river there, we have to follow the river. Okay. So, in this portion from here to here, or in terms of this here y that we want is equal to r, other portions it is a circle. Okay. So, here it is a circle and here it is a circle, because that would enclose the maximum area for a given length of the curve, that is we know as isoperimetric problem. So, by having a global constraint, we get this Lagrange multiplier lambda, other one we get this lowercase lambda. So, lowercase lambda is 0 in this portion, here it is 0 and here also it is 0. In between this region, this lambda, because the constraint is active, it is following the river profile, it will be greater than or equal to 0. Okay. And what about this capital lambda? That simply indicates the radius of curvature of this red curve, the y. So, Lagrange multipliers always have some physical meaning. This radius of curvature of the circle, radius of curvature of the circle meaning radius of the circle itself, radius of the circle that we have, that is indicated by this lambda, because that is what comes from the equation that we have here. So, we say for Chatterjee's problem circular arc is a solution, but whenever circular arc goes above the river profile like here, we have to follow the river, right. There the inequality constraint is active, then there will be a corresponding Lagrange multiplier coming in into the problem, then the curvature constant will not be true because this lambda then, okay, lambda here will not be 0, that will be variable, and that is why we follow the river profile which we have from here. Okay. So, we have solved a problem that involves a global constraint as well as a local constraint. In mechanics, this kind of subsidiary constraint has another use to solve contact problems. Let us say I have a beam which let us say is fixed at both ends, and I have a rigid obstacle of some kind here. Okay, there is a rigid obstacle. Okay. Now, when this beam deforms, okay, it cannot go through it. So, there it has to follow the profile when there is some loading that is applied on this, let us say some q of x, okay, then it has to follow, it cannot go into this obstacle. So, where it has to follow this. So, that can be posed here. So, minimize potential energy of the beam, okay. Here W transverse displacement everywhere, this W of x is the thing, minimize potential energy 0 to L, let us say this length of the beam from here to here is L, E second moment of area W double prime square minus 2 and then Q times W, this is the total potential energy of the beam which we had also mentioned earlier, subject to when we minimize potential energy we will find W of x to minimize that gives a static equilibrium solution, but then we have the problem that the W that we get has to be less than the gap function. So, here we can define a gap between the beam and the obstacle. Okay. We say that is G less than or equal to 0, right, W minus whatever gap that is different at different points that will be specified, and hence there will be a corresponding lambda here. This lambda turns out to be contact force here because Lagrange multipliers have physical meaning. Okay. It is a contact force, and that also makes sense when we write the complementarity condition that lambda times W minus G equal to 0 has two possibilities, either lambda equal to 0 or W equal to G. When lambda equal to 0, then W is less than G strictly, because this need not be 0 when lambda equal to 0. It can also be 0 in again in some special cases which you do not need to worry about right now. When W equal to G, this is already satisfied, then lambda we say is greater than or equal to 0. Okay. Then in this case it is active, whereas in this case this is inactive. So, contact problems can be solved using variational framework when you have function type constraints. Okay. So, we have solved a problem, Chatterjee's problem, example to show that how we can deal with inequality constraints which are function type constraints. We also see the same thing in contact force problems in mechanics, and that brings us to our structure optimization problem which we solve in the next class, which we noted at the beginning of this lecture, minimize strain energy which is 0 to h E A u prime square dx with half, and area profile is the design variable subject to governing equation is a function type constraint or a differential equation or local type constraint E A u prime prime plus p equal to 0 and then 0 to L A dx volume constraint, which is a global constraint, which we can put it now as a inequality constraint, right. So, whenever we put inequality, corresponding multiplier here lambda x and here it is, we use lowercase Greek letter for a function and we use uppercase Greek letter for a unknown constant. Whenever you have this, here also we can write complementarity condition lambda times the constraint 0 to L A dx minus v star equal to 0 and lambda is greater than or equal to 0. Just like in the previous problem, we wrote this lowercase lambda greater than or equal to 0 at every point in the domain. It is unknown constant, one constant is greater than or equal to 0 and this is the complementarity condition, complementarity condition, complementarity condition. Okay. This particular problem we will solve in the next lecture and also do some computations to see what are the optimal area profiles for this. That way we see calculus of variations with constraints now. In geometry we saw Chatterjee's problem, contact problem in mechanics. Now we also see this in optimal design. That is the demonstration that variational methods are useful in geometry, in mechanics as well as in design. Thank you.